Alright guys, so this is a little bit quicker. A little derivative. Just the product rule, and then you can take the e to the negative 2x squared out. E to the power can never equal 0. We know there's an asymptote at 0 for exponential functions. So that's not going to give me any critical locations. It's not undefined anywhere. So only this gives me the critical numbers. How are we doing so far? Is that okay? Still got my poker players out there, some of you guys. And then the sign diagram, there's only a couple of locations to put on this thing. We haven't got a problem yet where I put a little u, and we will for undefined, just haven't had one. Multiplicities, they're both odd multiplicities, so the sign's going to change everywhere. If I put a 0 in, what do I get? I get 1 times 1. So I get positive. And what's it going to be out here? Negative. And negative, because it's got odd multiplicity everywhere. It's going to change signs everywhere. I like it. So where is it increasing? Yeah, negative 1/2. It's 1/2. I love it. Decreasing, of course, everywhere else, just outside of there. So it does have a, so this goes down, up, down, so it's got a min and it's got a max. And whatever the hell you get when you plug 1/2 into that beautiful expression. There's no way in hell I'm gonna, well, let's see, I'm trying. You're not gonna do it, Jeff. I know. I'm not gonna do it. All right. So you just gotta plug stuff in. Eventually we're gonna round them down to 1 decimal place. We're gonna be graphing these bad boys by hand. So if you can graph 2 decimal places, you gotta show me. So if I do 0.5 times e to the negative 2 times 0.5 squared, right? Yeah, 0.303. That was for this one. And if I put negative 1/2 in, it's going to be negative 0.303. Kick ass. And again, it's not that it's wrong to plot this bad boy. It's not wrong to plot it. It's just wrong to copy what you see. Oh, I got a weird window. Oh, shit. Well, I kind of know I want my window to be kind of close in. So let's see, zoom 6. And then I'll make my window. Let's go from negative 2 to 2, and from negative 2 to 2 on there too, just because. So going down, going up, going down. It's crazy. Oh, a little bit glary. Okay. It's always nice to have verification. Now, if you plug it in the calculator wrong, you're going to start to second guess yourself. All right, how do we feel about all that? I mean, that's not horrendous. So the last thing for today, I think, I want to talk about something I've teased before. It is the idea of what does a second derivative tell you? So what's a first derivative tell you? Slope, I love it. First derivative tells you the rate of change of whatever the function is. So we need to get past the idea a little bit. Anytime I take a derivative of any function, I don't care where that function came from, I don't care what it represents, it is the rate of change of that function with respect to the input variables, right? So if I had a function that was watermelons, and the input was pounds of fertilizer, it'd be the change in watermelon per change in amount of fertilizer. For every extra little bag of fertilizer, how many more watermelons are eventually going to get to the less watermelons because you're piling too much shit. If my function happens to already be the first derivative of some other function, and I take a derivative of that, that of course is a second derivative. But anytime I take a derivative of anything, it means the rate of change of that thing. So if f prime is slope, f double prime is the rate of change of slope. I love it. And you hear this kind of thing, I think I pointed out to you guys, you hear this all the time in the news. The economy, the rate at which the economy is decreasing has slowed. You hear that kind of thing if you listen to any economic news at all. All it means is it's still going down, but not as fast. Right? And the reason that's important is we're hoping that the overall picture ends up looking like this instead of one of those, I just rested, screw you guys. Right? Maybe. So, second derivative. Where's my good marker? There you are. At the most useless way to say it, to be honest, is the rate of change of slope. And then you got to think, what the hell does that really mean? So let's look at a visual. So if I have, let me just make a really simple. So what is the slope back here? I don't even need to open you up. What is this? Tell me something about the slope back here. Tell me something about it. It's in green. The slope. Tell me about the slope. Not the function. The function is increasing because the slope is positive. I love it. I want you to see why I'm saying this because what is happening to the slope as I move this way? What is happening to the slope? The slope is decreasing, isn't it? You guys see that? So the second derivative, isn't it? It's decreasing all the way through. You guys with me? So like if I'm in a car and I'm going and I hit the brakes, what am I going to do? I'm going to slow down. Am I still going forward? Yes. I'm slowing down, but I'm still going forward. And then if I crank and go in reverse, now I'm going to start to go backwards. Right? But I'm always kind of like, I'm taking away from the slope. It's positive. I'm taking away from it. It's zero. I'm taking away from it. It's negative. So it looks like maybe the second derivative of this is actually constant. And think about it. If I had, this isn't quite what this is, but if I had this, what is f prime? Because it's like a down parabola. You guys with me? It's been shifted, but who gives a shit? What do I get for the derivative? And what's the second derivative? Yeah. And I don't know if you guys see, we're just starting to talk about this, but it feels like the slope is changing at the same rate throughout this whole thing. It's smaller and smaller and smaller at the same rate. I like it. That's that smooth, you hit the brakes and you hope your car, you hit the gas and you hope your car, continues. Instead of, jerk would mean that the third derivative exists. It's not zero. Here the third derivative is zero. There's no jerk. That's what you hope your car does. Of course, Jeff's old cars, it didn't look like this, right? Okay, that's beside the point. Keep shitting on my old cars because they were POSs. So now this is too nice to believe. Is everybody with me that the second derivative through this whole thing is negative because the slope is decreasing? Therefore, the function that talks about the rate of change of slope must be negative then. So around this whole thing, the second derivative is negative. So let's look at what if I had a smiley face instead of a frown, right? So what if I had... Yeah, what if, Jeff? I don't know. So what if I had this? Let me not even draw any scale or anything. Why not? So now, obviously, the opposite thing's going to happen. The slope here is really big. Negative. And what's happening to it? The slope, is it getting smaller or bigger? And I love you guys. Smaller means more negative. Bigger means more towards the positive. Right? So slope is really negative. Is it increasing, getting less negative, or is it decreasing, getting more negative? It's getting less negative, so it's increasing. That's the definition of increasing, less negative. And then over here is definitely freaking increasing, right? There's no question. So I want you to realize something. I mean, that's really all this is when I look at a function, if I want to figure out what f prime is doing, I just see where the function itself is going. How is the function itself changing? If I want to know f double prime, I got to think about how the slope is changing. So here's something remarkably cool. Here the slope of the first derivative. So the second derivative here is going to be greater than 0. It's increasing. You with me? This is almost too good to believe. So when the second derivative is negative, it's down. Cup down is what we call it. Would not hold water. When the second derivative is positive, it's cup up. It would hold water. You guys, see what I'm saying? So I want you to see this. This element is what we're missing. Let me really zoom in a little bit more here. Here's that last one we did. Do you see the concavity where this is coming in? Here, what's the concavity? Concave up or concave down? Here, is it cup up or cup down? Here.
It's debatable.
No, it really isn't. Would this hold water or not? Yes, if I poured water here, this would hold it, right? Does this shape look like an up parabola? Yes. No, yes.
Jim, your eyes is red.
I know. I said this earlier. Oh, you came in late. Look. Now get over it. It's okay. It's healing. Over here, this would be... So here, f double prime would be positive. It's cup up. Here, f double prime would be negative because it's cup down. Maybe. If you remember this point we were talking about way earlier, is actually where these two things could meet. That point where it's the most negative or most positive slope. Remember that? And we called it the inflection point. So what's a critical point? What's a critical number? It's where the slope might change from positive to negative. So a critical number for the second derivative, you need an R in there, Jeff. Second derivative critical numbers are where the concavity might change. And you see this in polynomials. You have all this, it's cup up, cup down, then it's cup up, and then it's cup down, then it's cup up. So anywhere there's a most negative or most positive slope in between those places, that's the inflection point. That's kind of like where one cup up, cup down, there's the inflection point right on my thumb. Yay, nay? That's a lot like the location of maxes and mins. So, I would have a picture like this. So this is definitely cup down. So in this region, f double prime is less than 0. In this region, f double prime is greater than 0. And somewhere right here, f double prime equals 0, because that's the transition place, the inflection point. Okay, maybe. And sometimes you hear about that where they're like, we think we've reached an inflection point in this blah, blah, blah. And they're hoping that it really does turn around, if it's the economy, for example. Or Trump's approval ratings, he's hoping it's going to turn around. Right? All right, so that's all for politics, sorry. Okay, so let's try a concrete problem out. Please, your guide, Jeff. Let's see. Oh, here we go. Let's try something a little more interesting. Yeah. Ooh, let's see if that's too interesting. All right, let's analyze the hell out of this thing. Everybody got this here, right? I'm going to make some more space. This guy looks really interesting. All right, let's just cut to the chase here. So I would start with analyzing first derivative stuff. So I want you to realize in pre-calculus, did you guys graph a little bit? You graphed like a shit ton, right? So graphing should be no problem for you now. Now we're learning more tools to make our graphs more precise. And you have got to let go of the fact that we have this magic black box that will graph it for us. For humans, the more we understand what it is about a function and how it relates to its graph, the quicker we can analyze any situation. So, if I want to find the max and mins and the increasing, decreasing stuff, I take the derivative. How do I take the derivative of this function?
Go to quotient or product. You can go quotient or product.
Yeah, quotient or product, I love it. Let's go ahead and do quotient rule, just because. So it'll be top times bottom, top derivative times bottom, minus top times bottom derivative all over bottom squared. So I get x squared minus 2x squared, so I get 1 minus 2x, gather 2. 1 minus x squared over x squared plus 1 squared. Oh, I love it. We still don't have a situation where we're undefined, though. Why is this never undefined? What's the smallest the bottom can be? 1. There you go.
Yeah.
Smallest it can be is 1, so it can't be 0, so therefore there's nowhere where it's undefined. Kick ass. Find the critical numbers real quick. Should be like, bam. Just look at it, write them down. Screw this, right? That doesn't give me any answers. Nowhere it's undefined, so I just have to look at the top then. So what are my critical numbers? Plus or minus 1, I love it. Okay, cool, I like it. So then I've got a little sign diagram. By the way, does the function itself have any weird places? Is there anywhere, what's the domain of this function? Very similar reasoning to what we just did. All real numbers. I love it. Okay. It's 0 here, 0 there. Multiplicity of 1, right? Be 1 minus x, 1 plus x. It's going to change signs everywhere. If I plug a 0 in, I get 1 over positive. So it's positive there and there. Blah, blah, blah. Therefore, it's decreasing from negative infinity to negative 1, or 1 to infinity. It's increasing from negative 1 to 1, right? This is all stuff we just did recently. I want to try to get to the concavity part, but I don't want to just bypass this. It's got a what here? Goes down to it, up from it. So this would be a min. Down to it, up from it. So min at -1 something. -1/2. And a max, become the word max, at 1 +1/2, I believe. Yes. Okay. Local min, local max, right? The absolute min is going to be -infinity. It looks like, wow. Okay, how are we all doing? For concavity, we do the same stuff we just did. We just do it for f double prime instead. So here I could have done down, up, down, and that would help me with the min and max thing. So when I go to concavity, I want to look at f double prime. Oh shit! What's f double prime? Oh smack! Derivative of the top, -2x times the bottom, minus the top times the derivative of the bottom, which is really yummy. It's going to be 2 times x squared plus 1 times 2x. Okay, let me stop there for a second. I know I'm not done with that. Derivative of the bottom, 2 comes down in front of this times the derivative of the inside. That's yummy. All over the bottom squared. Right? It was already squared, so now it's 4 power. So let's see what we get. Is everybody cool with this? This is where you got to be really careful about when you're allowed to do this. I can kill an x squared plus 1. Because everybody's got at least x squared 1 to x squared plus 1. So I can kill an x squared plus 1 because everybody's got it. I can't just kill it in one piece. That's illegal. Should have been gotten out of your system before now. So now I get -2x cubed minus 2x. Let's see, what's left alive here? 4x. So it'll be minus 4x plus 4x cubed all over. You're doing this a little quickly, Jeff, but oh well. All right, I'm just trying to get my stuff together. This times this is there. Minus 4x times this, so minus 4x plus 4x cubed. I love it. Looks about right. Everybody with me? This is just algebra cleanup. It's important still, but it's just algebra cleanup. So then I finally get, what do I get? 2x cubed minus 6x all over this business here. Find the critical numbers for that. So the phrase critical number does not only apply to the first derivative. It applies to whatever derivative I'm looking at. So find the critical numbers for the second derivative. I left something out now. No. No, okay. Oh. You gonna make it, dude? Maybe. It's not too horrible. You get not the prettiest things in the world, right? But still, there's nowhere where it's undefined. So the critical numbers for f double prime, you can take a 2x out, you get x squared minus 3. You get x is 0 and x is plus or minus rad 3. Is that cool? I like it. So those are the locations of possible whats. I think I saw somebody mouth it. Inflection points. I love it. I'm dealing with the second derivative. Its critical numbers are where there might be inflection points. I like it. So, how do I investigate it? Well, make a little sign diagram, right? Put this guy to bed. Sleep. Got my negative rad 3, and got my positive rad 3, and got my, oh, zero's been taken. Hate that. Oh well. What are my multiplicities? Any even multiplicities? You gotta get over the squared, because how do I get both of those? I break this up into x minus rad 3, x plus rad 3. All first multiplicity, so all odd. It's gonna change signs everywhere. So if I put in there, let's put in there a 10. Positive times positive, positive, negative, positive, negative. It doesn't matter what you put in. It doesn't matter what you get out, except for is it positive or negative. You don't care what the number is, right? Okay. So now watch this. This is kind of cool. What does this mean? What's that negative mean for this region? What's true about the function?
The slope is decreasing.
Okay, slope is decreasing, which means it looks like what? Cup
Down.
down. So it looks down. Sad, happy, sad, happy. Is that better? Like cup up, cup down? Sad because you're negative.